So Dr. Kane is a professor of planetary astrophysics at the University of California in Riverside, who specializes in exoplanetary science and planetary habitability. He received his Bachelor of Science with honors from Maguire University in Sydney, and also his doctorate is from the University of Tasmania. His work covers a broad range of topics related to planetary astrophysics, and he has discovered and co-discovered hundreds of exoplanets. That's amazing. Okay. He's a leading expert on the topic of planetary habitability, the habitable zone of planetary systems, and the study of why Venus and Earth underwent divergent evolution. Maybe not in the near future, no, we discussed that yesterday. He has published hundreds of peer-reviewed scientific papers, as well as several books on the topic of exoplanets and habitability. He's also a prolific advocate of interdisciplinary science through combination of biology, climate science, geophysics, planetary science, and stellar astrophysics. So it's a great pleasure for us to have you here. Thank you so much again for accepting our invitation. And Dr. Kane, please take the floor.
All right. Okay, well, thank you so much for that kind introduction. Well, that's a, this one will probably work as well. This is my, there we go.
Yeah, can you
yeah.
change the slide?
It's good. Thank you. Thank you for that kind introduction. And thank you for inviting me and to all of the organizing committee. It's such a pleasure to be here. I also note that on the schedule, I assume the schedule is still the same, that I'm the first and the last speaker of this conference. So the first and the last impression people are going to have, that's quite a lot of pressure, but hopefully I can live up to that. So as was mentioned, I study a lot of different things, and one of my favorite topics is the differences between Venus and Earth, and I'll be talking a lot about that over this week. So I have a summary slide of what I'm going to be covering this week, and I'm down for giving 4 different lectures, and tomorrow I'm going to be talking about Venus, and then I believe it's on Wednesday I'll be talking about stars and planetary energy budgets, and I'll explain today why that's an important topic. And then on Friday I'll be talking about the habitable zone and how interaction between planets can influence climates, things like that. But today I'm going to be mostly introducing this topic, and there will be parts of this that will feel a little bit like randomness and maybe a little bit rambly, because I'll be laying down some of the basics of what I'll be talking about the rest of the week, and just exploring some examples of some of the topics that come up in planetary habitability, because believe me, there are many. It is an extremely broad topic, as I'll show you today. So hopefully at the end of today's lecture, I'll give you some things to think about that I'm looking forward to having interesting discussions with you all during the week. But before I go any further, I did want to mention that a lot of the material that I'm using this week, I actually finally got down into print. It was actually a pandemic project of mine, where I had been asked before the pandemic to write a book on this topic, and I was reluctant for a while for a variety of reasons, one of which is time, but also it's a controversial topic, which I will get to. But in the end, I decided that I would do it, but as I mentioned, time was an issue, but the pandemic happened, and we had a lot of time, as it happened. So I managed to have it completed. Now, it's available here from IOP Publishing, and depending on what your institutional access to that publishing company is, it should be free. And so if you use this QR code and go to that website, then, like I said, depending on if your institution subscribes to the Institute of Physics Publishing, then you may see that, that you don't have to pay ludicrous amounts of money. Because believe me, it is ludicrous amounts of money, and I don't want any of you to have to pay a single red cent. So, if your institution doesn't have access, I've just made it available here. I essentially uploaded it to Google Drive. So if any of you want access to it, you should be able to access it via either of those links. And please don't pay any money for it. I want everybody here to be able to use it at zero cost. So I want to quickly ask, for those of you who are here, I think this would be useful not just for myself, but for the other speakers at this conference. How many of you have, would you say that your background is primarily in astronomy? Raise your hand. Astronomy, so we have a few astronomers. Biology, okay, a few biology. I'm going to separate out planetary science because normally within the culture, the planetary scientists definitely, well, anyway, there's a whole other discussion. How many people would more identify as a planetary scientist? All right, so there's a few planetary scientists. All right, geologists, a few geologists, and climate scientists, few waving of hands maybe. And did I miss anything? Did I? All right, sounds like I've covered it. But the point is that, you know, for each of those topics, it was pretty even number of hands, I would say, for each of those topics. And the reason I wanted to explore that, not just for my own benefit and benefit of everybody else, because that's a big part in this interdisciplinary discussion, astrobiology, which is of course a misnomer, because it's not just astronomy and biology, it's everything. But the language barrier and the way in which we talk to each other is a big part of this, in being able to cross these disciplinary boundaries. The other reason I wanted to ask that question now is because I will say that the book that I wrote is for a broad range of people. I teach a class on this at the graduate level, and I'm in an Earth and Planetary Sciences department, and I have a broad range of people, essentially people who are representative of all the different disciplines that I just asked about, coming into that class. And that's what this book is written for. And it's kind of a gateway book, because if you decided, I really like this, I want to go deep down that rabbit hole, then there are other books that do this really well. And that's why I've mentioned these other ones here. I will say that probably my favorite of these is Atmospheric Evolution on Inhabited and Lifeless Worlds. Quite a lengthy title, but David Catling and Jim Casting, and I think Jim was one of the speakers at a previous version of this conference. So let's move on, and I just wanted to introduce myself a little bit more. I have been studying this topic broadly for almost 30 years. I started grad school in the mid-1990s. And that was an interesting time because we were just starting to discover the first planets around other stars around that time in a way that you as a prospective graduate student could go to grad school and do that. It's hard to imagine now, but back then, if you wanted to do planets, then you mean solar system, right? That's what it was. But that was an interesting period, and so prior to that, my intention was to study the solar system, which ironically I now do. But back then, I decided to go into exoplanets, and so I've been studying this, discovering planets, as was mentioned, And it's been very interesting. But as time has gone on and we've discovered more and more planets, I've been able to get involved in characterizing planetary orbits and atmospheres. That's kind of like stage 2 of my research. And then I would say the past 15 to 20 years, so the majority of my professional career, it's become very focused on this topic of planetary habitability and the Hubble zone and how we define the Hubble zone, why the Hubble zone is even useful concept at all for us to talk about. So let's go back to the beginning, because we now know of more than 5,000 planets, and these have been discovered using a variety of techniques. I will say that I'm not going to really talk about the way in which we find planets over this week. That's a whole other interesting topic, which I'm happy to speak to any of you about, but I'm not going to be talking about that in the lectures. But suffice to say that we now know of many planets that are orbiting other stars, and they're enormously diverse. There's a huge diversity in sizes and masses. That is one of the primary measurables that come from our observations of other stars when we're discovering other planets, is the size and the mass of those planets. And we've found that of the ones that we've discovered, about 30% of those are gas giants. And when we look at something like small planets, we see that 4% number, which can be very disparaging. But something to keep in mind is that there's an observational bias there. There's a selection effect. Terrestrial planets are hard to find, very difficult to find, whereas your gas giants typically are your low-hanging fruit. And indeed, the very first planets to be found were these gas giant planets. They're just they have the largest effect on their stars, and so we can see them. But in order to do a really good job of finding planets, especially terrestrial planets, then a significant barrier for us is the Earth's atmosphere. If you're trying to do this from the ground, then trying to do precision measurements, particularly if it's the brightness of a star, then trying to do that precisely enough from the ground is very difficult. And so we go to space. And so in 2009, there was a mission launched called the Kepler mission. And the Kepler mission was the first ever NASA mission whose sole purpose was to find planets around other stars. That was the main purpose of that mission, not just planets, but terrestrial planets. It was really about answering this question of how common is Earth. And so this is an animation showing the Kepler spacecraft, which was deployed not into an Earth orbit like the Hubble Space Telescope, but into what's called an Earth trailing orbit. So it was deployed close to a Lagrange point where it follows the Earth around the Sun. And the reason that it was deployed so far was because this was a mission that had to stare continuously at about 170,000 stars for a period of 4 years in order to detect planets that pass in front of their star, something which we call the transit method. Now, that was the Kepler mission, like I said, 2009, enormously successful. And more recently, we now have a mission called the Transiting Exoplanet Survey Satellite, or TESS, and that mission is actually in an Earth orbit. Now, it's kind of a follow-up to Kepler, but not really, because Kepler, like I said, stared at 170,000 stars for 4 years, just a small patch of sky, and looked to see how many of those stars might have planets. TESS, on the other hand, because it's anchored to the Earth and following the Earth around the Sun, it's scanning the sky. And so what this is showing is a map of the sky that the Transiting Exoplanet Survey Satellite is measuring the sky. and how long for. So you can see this is 27 days, 54 days, and so on. And as you might imagine, the longer the period of time that you stare at a star, the longer the orbital period of the planet that you can discover. Because Earth, for example, takes 365 days to orbit the sun. So if we were to stare, if we were an alien civilization and we were staring at our sun and we only did so for 27 days, the probability that we would just happen to see the Earth cross the disk of the sun during those 27 days is very, very small. 1 in 12 as it happens. And so you need to be able to be staring at these stars for a long period of time. So that's just a quick summary of some of the main missions which have contributed to the discovery of exoplanets over the past several decades. Now, there have been others, and at the end of this lecture, I will give a summary of what's coming in the future. But there's a point I want to quickly arrive at here, which is that one of the main discoveries from the Kepler mission was actually that the occurrence of small planets is very large. Now, you recall that diagram I showed you earlier showed that 4% of the more than 5,000 planets that have been discovered are terrestrial. That doesn't mean they're rare, it just means they're hard to find. But when you calculate out the observational bias, then what you actually discover is that the occurrence rate of planets increases to smaller sizes dramatically. Small planets are much more common than their larger planet counterparts, which kind of makes intuitive sense in the sense that if you can imagine a pile of rubble, there would be a couple of the large boulders, and there would be many more of the large rocks, many more of the smaller rocks. By the time you get to the grains of sand, you can't count them anymore. Turns out planet formation works in exactly the same way. Planet formation is making many more of these smaller planets. And so this is a gallery of some of the discoveries from Kepler, and you can see we've got Earth for comparison over here on the right, and so these sizes are proportional. And we go all the way up to Kepler 22, which incidentally was the location in a science fiction show by Ridley Scott called Raised by Wolves. So already these kinds of planets are entering into the nomenclature of science fiction. But this is twice the size of the Earth, and I'll get back to the significance of that in a moment. We're seeing the diversity of these different kinds of planets. Now, another thing you'll also see is that we seem to have extraordinarily high-resolution images of these planets. Except that we don't. These are all artist impressions. All of these planets have been discovered using what's called an indirect technique. That means we don't see the planet. We infer the existence of the planet based on observations of the star. And then we use things like the size of the planet, how much energy it receives from its host star, to infer things about the planet, whether it might be habitable or not. But in reality, we don't know. Planets are complicated, and that's going to be one of the main takeaway messages from this first lecture. Planets are extremely complicated, and when we try to make this kind of leap, then we can run into a lot of trouble. Now, there's a bit of backstory to go through here, because this has led to the topic of planetary habitability being one of the most, I would say, controversial topics in all of astrobiology. And it goes back some time, because you have to remember that when we were finding planets, like I said, we found the giant planets first. When I started grad school in the mid-90s, I was finding planets, the massive Jupiter. And there were many discoveries like that. But then as we approached the era of Kepler, in 2006, 2007, people started to discover planets that might actually be rocky. And that created a lot of excitement because it meant that we could start talking about aliens. We could start talking about aliens from people who are astrophysicists, who are not biologists, and they're not even planetary scientists. Because what you need to remember is the whole topic of exoplanets originated from stellar astrophysics, not planetary scientists, for the most part. And so it was stellar astronomers who had been looking at things like eclipsing binaries for over a century and realized that they could do the same thing just for smaller objects. And then when we started to discover planets that could be rocky and were far enough away from their star, then there were some press releases that can only be described as hyperbolic. And so, when we look, for example, at the case of Gliese 581, which had a series of planet discoveries associated with it during the 2000s, and there were some press releases during that time that the discoverers were going and talking to the media and saying there is a 100% chance that this planet has life on it. An outrageous claim. And in a follow-up interview, one of the people involved was asked, well, you said 100%. Did you really mean 100%? And they said, no, it's probably more like 99.99%. Which meant that now they were claiming to several significant figures on whether there was life on this planet or not. And there were many other similar cases. I mean, there's the case of the TRAPPIST-1 system, which I'll talk more about. TRAPPIST-1 is a very famous system. It's a system of 7 known planets around a very, very small star. And this is an artist's impression of from the surface of one of the planets, where you can see the star, you can even see the other planets obvious in the sky because it's a very compact system. But artist impressions like this, although they are very inspirational, they can also be dangerous, and they led a lot of people to assume that this meant that we knew that there was life on those planets. Now, there's been a lot of pushback on this from certainly within the scientific community, but also there are some members of the media who have started to see through this for many years now. This is an article from The Conversation from some years ago, where they're saying, until we get better tools, excited reports of habitable planets need to come back down to Earth. And the article is all about how a lot of the press releases have been, at the very least, hyperbolic, but at the worst, that hyperbole can lead to an actual degradation of the science, because it means that we're making claims that we haven't made yet. We're kind of scooping the discoveries of somebody 30 years from now who will make a discovery, a definitive discovery, that that planet has a viable ecosystem on it. But we're not there yet. We're not there yet. We need to be prepared for that. But it was interesting seeing these kinds of articles coming out. And there was a colleague of mine, Elizabeth Tasker, and we've had many, many conversations about this, about the discourse about planetary habitability and about the way in which we talk about it, and how we should be very, very careful when we're talking about a habitable planet, or rather a potentially habitable planet, one that deserves further follow-up observations. And then the conversation can be about, well, what observations do we need to do in order to confirm this claim? And that's where the conversation, of course, needs to go. And that's where I hope to take you over the course of this week. And so, leads to this question about what is planetary habitability? Well, planetary habitability, that is a question that is the kind of question you could ask 10 different people and get 13 different answers. Because it depends on what you're talking about. If you're talking to an ecologist, for example, then an ecologist will tend to have a macroscopic view of this kind of a subject. They will have done an incredible amount of studies into Earth-based ecology and what could be considered habitable environments, particularly things like extremophiles, which can survive extraordinary circumstances that would normally be out of the range of what we might consider. There are even people who've done a lot of work on things like tardigrades at the International Space Station and other locations, and looked at the resilience of some of these species. So there, you can think about the tolerance of life in somewhat of a Gaussian distribution, and when you look at the wings, you can see some extraordinarily resilient cases. So when we talk about what is planetary habitability, there's different viewpoints that you can be coming from, because on the other hand, an astronomer will talk about planetary habitability in the context of, I want to be able to measure a planet that I can't see that is 10 parsecs away. That is a diametrically opposed viewpoint, or at least starting point, from the ecologist. And so when it comes to talking about this topic of planetary habitability, there needs to be some kind of framework from which you can start at. And like I said, this whole topic of planetary habitability has become very, very, very controversial. For example, when I will talk to some of my colleagues, whether they be astronomers or whether they be planetary scientists, I kind of sit in the middle of those two, or in both of those camps. And I'll talk to a planetary science colleague, and they will say the whole topic of planetary habitability is nonsense, because there's no way that we know that these exoplanets that have been discovered are habitable. And what I can say to those colleagues is, you know what, you're absolutely right. They're right. Let's talk about how we fix that. All right, let's talk about what we do next. What are the observations that we need to do to actually make this work? All right, so planetary habitability. Some things to think about. Now, planetary habitability, the way in which I think about it as a planetary scientist, is what I care about is the planetary energy balance model. And so what I mean by that is, as I say here, an assessment of the energy balance of a planetary surface. What is controlling what's going on at the planetary surface level? In particular, temperature. What is controlling the temperature at the planetary surface? Not just at the present epoch, but over long periods of time. How do you sustain long-term temperate conditions on a planet? And then there's all these questions about, well, what makes a planet habitable? If there are many aspects which are controlling that energy balance, which ones are those dominate? Some of those will be very important, and I'll be talking about some of those in particular. Some of those are very interesting, but maybe they're third order, or maybe even fourth order effects. And so that's what we need to identify. What's controlling this energy balance? What measurements do we need to make in order to be able to determine this from a very large distance? Astronomy is intrinsically a remote sensing science. You can do work in a lab, and there's a lot of planetary science and astrophysics that's done in the lab. But ultimately, your measurements are from objects which you're probably not going to have a lab there, you know, unless you're on the MSL team or something like that, one of the Mars teams. So what can we do with these measurements? How can we use them to infer the conditions? How can we apply this to planets inside and outside of our solar system? And I'll talk about the differences between those two. And of course, the anthropic principle this whole idea is that what we're measuring is because we're here, but the whole bias of when we're having these discussions as the occupants of an ecosystem that has been around for more than 4 billion years, of course we're biased. And we need to be prepared for that. It's one of those topics in astrobiology where people say, well, we don't know what we're looking for, but we'll know it when we see it. Will we? Will we know? Will we know it when we see it if we're discarding data that is outside of our bias? Of course, we need to be open-minded about this, but on the other hand, Earth is a very integral starting point. And when we're talking about starting points, then one of the topics that we always go back to is water. All right, so we want to construct a framework for an energy balance. We want to know what is controlling the temperature at the surface through time. Where are we going to start? Well, a very common starting point is the presence of surface liquid water. Now, there's a lot of bias associated with this, of course, with the utility of liquid water. Liquid water has been extremely important for the presence of life on Earth, extremely important. And there are some people who argue this by saying wherever you find water, you find life, on Earth. But I would say that the Earth has been completely contaminated at this point, after 4 billion years, such that wherever you find anything, you find life, such as the tardigrades being able to survive in space for a period of time. I mean, this is why we have to work so hard to decontaminate anything we send to Mars, so that we don't spend these billions of dollars to send delicate instrumentation to Mars only to detect something that we brought with us. So it's a difficult problem. But, like I said, water has been very important, and there are some good reasons to like water in a liquid state. First of all, it's extremely common. It's extremely common. Hydrogen and oxygen are intrinsically common. They're preferentially, hydrogen is intrinsic to the universe, but oxygen is preferentially produced in the cores of stars. And so the dihydrogen monoxide molecule is extremely common. And if you think it's common here on Earth, you wait till you see the outer solar system. There is tons of water out there. And then you wait till you see the interstellar medium. There's water everywhere. So that's a great plus, because you want something that's going to be a neutral solvent for biochemical reactions, and water is just a nice go-to. But there's another reason why water is a nice go-to, especially for biochemistry, and that's because it's a liquid state at reasonably high temperatures. Because you can start to think about other various possibilities that are usually in a liquid at much, much lower temperatures. And so water is extremely nice for that. And so what we can try, if we're going to construct this framework, is using a definition, the ability of a planet to retain surface liquid water. Now, I'm going to emphasize the surface part of this. I will speak a little bit about things like icy moons, something which may have a subsurface ocean, and talk to the challenges of that. But for now, let's just say surface liquid water. And as I say here, this creates a framework from which we can quantify an energy budget of a planet. And importantly, this is applicable to large distances for planets that we'll almost certainly never visit. And that's one of the things to keep in mind. When we're talking about, say, for example, Proxima Centauri b, which is by definition the nearest exoplanet. And that planet is in the habitable zone, by the way. We're not going there. We're not sending a lander to Proxima Centauri B, or probably even a flyby. The way I sometimes word it is that all stars, other than the sun, of course, are at a distance of infinity, basically, for intents and purposes of actually going there and getting a sample. And so that means that we're relying on measurements that are going to be over large distances and remain over large distances for the foreseeable future. So that's very interesting because it means that it means that what you're trying to do in this framework is maintain a surface temperature of between 0 and 100 degrees, approximately. And we can talk to that. Now, what are the factors that affect the presence of surface liquid water? Well, remember how I said planets are complicated? Yeah. So this diagram actually has a nickname. It's called the planets are hard diagram. I think it was created for the purposes of intimidation, basically, to scare the hell out of grad students. But you can see it's been divided into 3 main categories. We have the properties of the planet itself, and there are properties of the planet such as the mass, the radius, the albedo, the reflectivity of the planet, and then you've got the atmosphere, there's composition, there's chemistry, there's all sorts of things going on there. You've got the interior, whether your planet is still volcanically degassing and contributing to that atmosphere. You've got the surface and all of the processes that are occurring there, and then you've got the orbit of the planet. But then there's 2 other categories. There's the planetary system, because planets are rarely alone, and so there are other planets that are there that might be affecting the orbits of the planet you're interested in. Maybe that there's other processes there, and I'll be talking more, particularly on the last lecture on Friday, about how having other planets can be beneficial in terms of volatile delivery, meaning, remember that water I mentioned that's hanging around at the outer parts of the solar system? We can get some of that if you have other planets that are also out there. But then, of course, there's the effects of the star itself. And the star, we'll be talking about that, my lecture on Wednesday, I believe. That's where we're talking about the effect of the star on the energy balance, because the star is usually the main contributor of energy to that balance. And there's a lot of factors to consider with the star. I mentioned earlier the TRAPPIST-1 system, where the planets are orbiting a very, very small star. There are consequences to that, as we will see. But one of the things that this diagram doesn't tell you is the thing I mentioned earlier, which is what are the relative contributions to these? It shows you a whole bunch of things to think about, but it doesn't tell you which ones you should be paying attention to, and maybe which ones you can kind of ignore. And so that, I think, is the main challenge of planetary habitability, which is trying to understand which of these dominate. Now, knowing which ones dominate is only part of the problem, because the other part is, although there's a lot of things listed here, and I'll say that this diagram is incomplete. There are a lot of things that you can think of that aren't shown here. So it's not even showing everything here, but the challenge then is, okay, if you pick out a particular item, can we measure it? And the answer is not always yes, and that's a problem. And so if we now look at, this is a table that I made, which you can find in the book, of some examples of some of the things that we can measure and some of the things that we can't. Now, the things that we can measure, and we can argue about some of the things that are in bold and aren't in bold, how well we can measure them, but this is kind of an approximation of where we're at, which is those in bold are ones that we can kind of measure. Now you see, for the star, we can do pretty well with the stars because we can see them. So in a lot of the data from exoplanets, in studies of exoplanets and discovery of exoplanets, it's stars. It's studying the star and inferring everything else, usually. And so we can measure things like the mass, radius, and temperature, and I'll be talking more about that on Wednesday, about unlocking these properties. But when it comes to the planetary properties, it's pretty limited. We've got the mass and the radius. From the mass and the radius, you don't measure a bulk density. What you do is you calculate the density based on the mass and radius of the planet. But then you've got all of these other things like atmospheric composition. Atmospheric composition is something that we're starting to really get into, especially in the era of James Webb Space Telescope observations. Atmospheric dynamics, pressure, temperature profiles. I mentioned here age, insofar as you can measure the age of the star, which is very difficult to do, then you might be able to get an estimate of the age of the planet. Planetary system, it's mostly some orbital properties, but there's a lot of gaps that are left. And so I'll be talking more about some of these items, like which of those are important, which are maybe not so important, and which ones we can measure. And just a quick aside on the topic of water, I said liquid water on the surface. I didn't necessarily specify a temperature or pressure. I mentioned the 0 to 100 degrees, but that's of course assuming Earth. Whatever random exoplanet you're talking about, it's unlikely that it has a 1-bar atmosphere. And so we need to consider the phase diagram of water. Okay, so what can we get away with? And those of you who have done any hiking up into the mountains and then tried to make yourself a cup of tea, you know the problem, which is that if you decrease the pressure, then the temperature at which it boils drops, and you rapidly diminish here. And this is, of course, the problem of Mars. Mars has a very low surface pressure. It's 0.006 bars, 0.6% of the Earth's atmospheric pressure. And so Mars has a very, very difficult time sustaining surface liquid water because it disappears off the end of this phase diagram. On the other hand, we could consider exoplanets that have higher pressure, and then we start to open up the temperature space, and we can even start talking about planets which may have a significant water interior under high pressure, but it can still be in a liquid state. Now, of course, there is a limit here because you hit the critical point where the vapor and the liquid start to be essentially coexist with each other. So there are limits to that. But this is just to say is that we shouldn't necessarily lock ourselves in to 1 bar of pressure because we might be missing out on other possibilities. So how are we going to detect the presence of these atmospheres that could sustain a temperate surface condition? And when we're talking about remote sensing for exoplanets, it usually comes down to the atmosphere. I sometimes describe the atmosphere of a planet as kind of like the campfire around which we can all gather and tell our stories. From all different disciplines, we can all gather around the campfire of an atmosphere, because the atmosphere is our measurable, really, for exoplanets when it comes to inferring whether it actually might have surface liquid water or not. The composition, a pressure temperature profile, and inferring the pressure at the surface. And one of the main ways in which we're able to do that right now is, of course, this is an animation of the deployment of the James Webb Space Telescope. And as you can see, it had hundreds of possible points of failure. And they all succeeded, which was incredible. I don't know if how many of you stayed up to well, I say this as a Californian, but for me, the launch was I think 4 a.m. on Christmas morning, which meant, you know, I was staying up for Santa Claus anyway, but I stayed up and I watched the launch, and it all went extremely successfully, and thank goodness it did. And it's been very successful in what it's been able to do so far. So how is it doing these measurements of an exoplanet that we can't see? Well, here is an animation showing the effect of an exoplanet passing in between us and the star. And what's actually happening is when this planet is passing close to its star so that from our perspective the planet transits, then what happens is the light from that star passes through the atmosphere on its way to us. And so the atmosphere of that planet essentially becomes a gas cell, which is an absorption experiment. And so we're looking at the absorption features of the starlight by the time it reaches us. Absorption that has occurred due to particular molecular species from the atmosphere of the planet. And what we obtain from that is a spectrum. And so you'll have a spectrum which looks something like this. This is, of course, Earth. Now, we have to remind ourselves again not to get too anthropic about this, but this at least gives us an idea of some features which we would find very exciting because they speak to the planetary habitability of Earth. We've got features like that of vegetation, and we've got oxygen and ozone. But then over here, you see there's all these water vapor bands, these absorption features due to water vapor in the atmosphere, and it says suggest habitability. Not necessarily the case, particularly when I talk tomorrow about Venus and about whether we would identify Venus as being different from Earth. But that is at least a good starting point. So these are going to be the features that we're going to be looking in the short term. We'll have the mass and the density of the planet, and from the density we can infer whether it is terrestrial or not, and from the spectrum, hopefully we can get an idea of whether a temperature pressure profile of that atmosphere can allow for the sustained presence of water at the surface. All right, so now I'm going to just, let's see, how much time do I have? I know we started a bit late, so 15 minutes? Okay. I'll run quickly through just a couple of examples of things that you can think about for this topic. And I'm going to start with an example from the TRAPPIST system. So the TRAPPIST system, as I mentioned, is quite a famous system. It was discovered by a Belgian, and if you've ever been to Belgium, then TRAPPIST is actually a well-known Belgian beer, an IPA. It's not bad. Oh, really? I haven't tried TRAPPIST 3. So I have a bunch of TRAPPIST 1 beer bottles in my office anyway. But, so TRAPPIST system is well known because of the fact that it has 7 known planets. There could be more, but it has 7 planets that we know of, and they're all terrestrial based on their radii masses. Now, the exciting thing for this system is that the green is representing the habitable zone, which I'll talk more about on Friday. And from this, it was inferred that there 3, maybe 4 of these planets could be considered to be in the habitable zone. And you can see these artist impressions that have surface liquid water and various things like that. Now, you can also see it's very, very compact. If you were to put this in the perspective of the solar system, it's miniature. It's well inside the orbit of Mercury. So they're very close to their star, but that's okay because the star is tiny. And so maybe that's okay. But stars that are tiny are also very, very active. And one of the concerns, which I'll talk more about on Wednesday when I talk about the effect of stars, is that the activity of the star could actually remove the atmospheres of the planet. And as we just saw, we need that atmosphere. We need it to have the surface liquid water, and we need it to measure it, goddammit. So without the atmosphere, we've got nothing. And the planet has nothing. It's a bare rock. And so that was one of the first targets of the James Webb Space Telescope. We needed to look at the TRAPPIST system and figure this out. So the easiest one to measure, TRAPPIST-1b, the planet which is closest to the star, was observed early on in JWST operations. And it's not good news, I'm afraid, which is to say that the planet was measured, and they measured the temperature of the planet as it passed behind the star as well as in front. And what they found was that that is consistent with the planet having no atmosphere. In fact, they say the most straightforward interpretation is that there is little or no planetary atmosphere redistributing radiation from the host star, and also no detectable atmospheric absorption from carbon dioxide or other species. So that was quite a blow to discover that the innermost planet not only is it not habitable, although we weren't really expecting that one to be habitable, but it doesn't even have an atmosphere. That's all right, we've got other planets. TRAPPIST-1c. So TRAPPIST-1c, these results came out last year. And in this case, what they tried was using different models. Now, this one is further out, and so you might even consider this one could be a good analog for Venus. That would be very, very interesting to discover a planet which is in the same evolutionary state, maybe with a thick carbon dioxide atmosphere. And so they tried several models. And so we've got a yellow model here. This one is representing modern Venus. And then we've got a green line here, which is, as it says here, bare rock with no atmosphere. And then we've got blue, which is a thin carbon dioxide atmosphere. And what they found is the error bars are large, right? So it's ambiguous. We're not sure what the answer is yet, but this is so far consistent with the sea planet also having no atmosphere. So one of the things that is going to be useful in the search for life is eliminating those planets that are bare rocks. I mean, that's kind of the process of elimination is definitely the glass is half empty way of approaching this topic, but there are a lot of targets, and it's important that we do this, that we don't waste time on the planets that aren't really a possibility. So what about the rest of the TRAPPIST planets? Those are yet to be observed or are currently being observed. They're more difficult because they're further out, and of course they're the more interesting ones. So we'll see. There might be hope. But this whole topic of the atmosphere being lost is a topic where we can go back to our solar system and think about Mars. Now, when we think about planetary habitability, sometimes you'll hear people say that you only have one data point. That's the problem with planetary habitability. We only have one data point. Nonsense, I say. We have several data points. Earth is habitable. But knowing where the boundaries of habitability are from places where we can go and analyze rocks at the surface and things like that is extremely important, because the boundaries are defining where your search space elsewhere. And so Mars is an example. We've got a planet which is half the size of the Earth, 60% further away from the sun. Why isn't it habitable? Well, it may have been for some early period. But one of the issues with Mars is, with it being small, is the loss of its atmosphere. Now, I mentioned earlier that it has a very low surface pressure. That's the surface pressure now. But what was the surface pressure of Mars? I'll tell you that the estimates now are that it could have been as high as about 0.6 of a bar, 60% of Earth's current atmosphere, early in its history. But Mars is extremely prone to the solar wind. And what this is showing is data from the MAVEN spacecraft. And this is a simulation showing this what we call non-thermal loss from the atmosphere. And the results from the MAVEN spacecraft, which has been observing Mars for many years now and looking at the effect of solar wind, matches exactly the model. We now understand quite well the atmospheric loss of Mars's atmosphere, and that is extremely useful to apply that to other planets. But it's also just something to be aware of, that even though Mars is 60% further away from the sun, it can still have these dire effects. And so sometimes when I talk to my graduate students, I'll ask them, what is the problem with Mars? And I'll say, it's too cold. I'll say, okay, let's put Mars in Earth's orbit, right? We're going to do a sneaky switcheroo sometime when nobody will notice. We're going to put Earth in Mars's orbit and Mars in Earth's orbit. So what is that better for Mars or worse for Mars? I'll say it's better. Say no. If you move Mars closer to the sun, then even what little atmosphere it has left will be gone. And so it's something to take into account about the effect of the star on the atmosphere. You've got to keep your atmosphere. So another topic I wanted to touch on here is planet size. Now, Mars can be considered the lower limit of planetary habitability, half the size of Earth. The truth is somewhere in between, by the way. Like you could think about, well, what about something which is 70% the size of Earth? I have a graduate student named Michelle Hill who's working on this, and her estimates are actually about halfway between Earth and Mars, 75%, for it to be able to sustain its atmosphere for a long period of time. But what about going in the other direction? Well, this is a plot from the discoveries from the Kepler mission. It's showing the size of the planets in Earth units with respect to the orbital period. And there's units of measurement here, Earth, Neptune, and Jupiter. And you can see that there's a lot of planets here in between Earth and Neptune. And that's really interesting because we don't have that. Our solar system has this interesting dichotomy, which for the longest time, before the discovery of exoplanets, we thought was real. That is, the largest terrestrial body in our solar system is Earth. The smallest gas giant is Neptune, and there is a giant gap in between. The terrestrial planets and giant planets are even grouped together, like physically. And so we thought that dichotomy was a natural consequence of planet formation. What exoplanets has taught us is that that is not true, that there is a continuum between Earth and Neptune size. And for that reason, we don't know what to call those planets. You'll hear words like silly phrases like super Earth and mini Neptune. It's because we don't know it. But if we go back to the picture of earlier, like these are just some examples, right? And we went up to Kepler 22b, and that's twice the size of Earth. How come we don't have a planet that is twice the size of the Earth? It's an interesting problem. But it's an interesting problem of like why we don't have that. And there's a lot to be said about that. But the consequences are is that it's very, very difficult to model those kinds of planets because we don't have an analog. And so when we start talking about one of the many, many exoplanets that is like 20% larger than Earth, 50% larger than Earth, what does the surface look like? What are the conditions at the surface? Doesn't even have a surface. When does something stop being terrestrial and start being a gas giant? It's a really difficult question to answer. And just as an example of that, the case of Gliese 1214b. This is a planet which has the size of 2.75 Earth radii. So it's between Earth and Neptune, quite a bit more towards Neptune than Earth. It was discovered in 2009, the same year that Kepler launched, but it was a ground-based discovery, so it preceded Kepler. And it was very exciting because it transited, which meant that we had a radius, a mass, and a density, and so it provoked a lot of models. And this is a model that was produced from a paper by Rogers and Sager in 2010. And in this paper, which is really great paper because it's an interesting detective story, where they are trying to deduce what the interior could be like based on what we know, which is almost nothing. We know the radius and the mass. And so what they started with was from the primordial material, whether it be rocks, primarily ices, or gas, you can have these different outcomes. And what they found is that it's degenerate enough of a problem that you can have the interior of the planet be more like Neptune, so more gaseous phase. You can have a water world where you can have substantial interior inventory of water, or you could have an outgassed super Earth where you have a smaller planet but it's degassed a large atmosphere. And we don't know which one it is. Now, that is a big problem. But the way in which I sometimes put it is that if we did have a planet which was twice the size of Earth, I want you to imagine with me, I undo everything that you've learned about the solar system almost. We can list the planets of the solar system, okay? Mercury, Venus, Earth, Mars, Phaeton, Jupiter, Saturn, Uranus, and Neptune. Phaeton, you know Phaeton, like it's up right now. Haven't you seen it? It's this very, very bright blue disk, this beautiful planet, twice the size of the Earth, that orbits the sun between Mars and Jupiter. And as somebody who studies Venus, and I know that my Martian colleagues feel the same, that there always seems to be going funding to the Phaeton community. They're always taking out mission money, and there's several probes orbiting Phaeton right now. What am I talking about? There was a original proposal that there was originally a planet called Phaeton that orbited the sun between Mars and Jupiter. The original asteroid discoveries were purported to be the remains of Phaeton, a planet that was in that location. But if we had that planet, and we all remember when that European mission deployed its probe and it entered down into the clouds, and we did not know if it was going to hit a rocky surface or not. And the data that it was gathering all the way down, and we saw the temperature and the pressure go up and up and up and up. Was it going to hit a surface? And we held our breath. We will never have that experience. That alternate universe I'm talking about will never, ever exist. That data we will never have. As I said, Proxima Centauri b, we will never know because we're not going there. Some people say, well, not with that attitude, but but this is a real problem, right? Because we don't have that laboratory here in our solar system to perform these experiments. And so I would say that the lack of a Phaeton is one of the fundamental problems with planetary habitability, because we know there are so many planets that occupy that size range. All right, so just a couple more slides and then I'll be done. And I won't talk a lot about this because although we don't have a phaeton, we do have a ton of giant planets. And we should be thankful for that at least, because we're rare. Only about 10% of planetary systems have any kind of giant planet beyond the snow line, meaning distance further from the star. Only about 10%. So we are in the minority. And we've got 4. We feel very greedy now, but that's very important. And I'll talk more about that on Friday when I'm talking about the effect of planets on the habitable zone. And the effect of the moon. I'm mentioning some of these in passing because I may not get time to talk about a lot of these, but a fascinating topic, speaking of being anthropic, is the moon, because it's another one of these cases where you could say, we are here, the moon is here. There's got to be a connection. And, there are some connections. There are the effect of the moon on tides and the concentration of biochemistry in tidal pools, things like that. And the effect of the moon forming impact on the water inventory of Earth is extremely important. So it's a question of whether the moon is critical for the presence and evolution of life on Earth, because if it is, then we have a real problem, because that's a low probability event forming the moon. Speaking of moons, another topic I won't get to go into a great detail this week, but I just wanted to mention it because it is important, and that is just moons in general. Icy moons, in particular, Europa and Enceladus and subsurface oceans. Part of the reason why I won't be talking about those in great detail is because of this remote sensing issue. Europa and Enceladus are extremely important objects to astrobiology within our solar system. Certainly, if there are independent occurrences of life on those, it would be very, very profound. But if there were a subsurface ocean on a moon orbiting a giant planet that's orbiting another star, that's another case where I have to cynically say we will never know, because there's no measurable. Even if we could detect that there was a moon, we're not going to send a Europa clipper to another planetary system. and so it's extremely important for our solar system. But for planetary habitability, it's a difficult one. So I know I'm kind of out of time, so I'll just skip this slide and just give a quick summary of what's coming up. So I mentioned a couple of missions so far, and this is showing both NASA and European missions, and some of these are in the past, of course. Hubble is still going, Spitzer has retired, Kepler has retired, TESS is going, JWST is very much going. Roman is essentially on the launch pad, and that's going to be directly imaged some giant planets after its launch. But then it goes into the vague future, and you may have heard of the phrase the Habitable Worlds Observatory, which is very much looking to the future of several decades from now on being able to produce a mission that can directly image an Earth. And that's going to be really important. In the meantime, the European missions, Crow, Gaia, and Cheops have all contributed a great deal to the discovery of exoplanets. Plato is launching soon, and then we've got Ariel, which is going to be measuring exoplanet atmospheres. But the planetary missions are also extremely important. This is where I spend a lot of, or most of my time these days, is thinking about the missions to the other planets. And next time, I'll be talking to you a lot about Venus, about why we're going back to Venus after all these years, and why Venus is so important. What's not shown on here is, this is Uranus out here, but one of the main recommendations of the last Planetary Science Decadal was actually a Uranus flagship mission, which would be amazing because it wouldn't just be an orbiter like the Voyager 1 and Voyager 2 spacecraft. I remember watching the results of those coming in. It was one of my main inspirations when I was a kid in outback Australia. But the Uranus mission, if we can pull it off, will be an orbiter, and it's gonna, yes, we're gonna probe Uranus, yes. And so, by the way, a lot of people in the ice giant community have argued against the Uranus mission just because they don't want to deal with the late night talk show host jokes every single night. I actually think that's free publicity, but there you go. But a lot of these missions that you're seeing here, when you look at the science they're doing, they're astrobiology missions. When you look at what they're measuring on the surface of Mars, or the heliophysics for the sun, and as I showed you, the sun can have a profound effect on planetary atmospheres, these are all astrobiology missions, some of them more obvious than others, things like Europa Clipper, like I was just talking about. But there is astrobiology science in all of the planetary science missions, and I'm happy to talk about any of these missions with any of you during the course of this week. So I'm just going to leave this slide up. This has just a complete throwing things against the wall and seeing what sticks sort of list of questions that you can think about. And the final thing I mentioned here is, which is what I always come back to, is what observations, measurements do we need to make to test ideas about planetary habitability? Tony was asking me earlier, am I an observer or a theorist? And I said yes. It's because I love talking about the theory of this, but I'm always also thinking about ways in which we can actually do it, if not now, then sometime soon. All right, I'll finish there and open up to any questions if we have time. Thanks.
Thank you, Stephen, for this great lecture. Thank you. So, questions? Don't be shy.
Thank you, sir. I'm learning a lot. I've worked for many years, Stephen, and for all of us, on the origin of life. And I'll be talking today and tomorrow. I think there's reasonable grounds to say that life requires chemistry, complex molecular reaction systems. You may or may not be persuaded tomorrow. But if that's true, when you look at the atmospheres of a planet transiting, what kinds of molecular complexity can you detect in principle in the atmosphere? I mean, can you understand my question?
Yeah.
Can you see complicated molecules and a diversity of complicated molecules or not?
Yeah, that's a good question. One thing I will say about that is a challenge for now. The way in which we're measuring atmospheres now, as I showed you in that animation where the light is passing through the atmosphere of the star, that is limited to where the atmosphere is transmissive enough that you can actually collect photons. It quickly becomes opaque as you descend into the atmosphere. And so what that means is that you're not measuring, for example, the troposphere. You're measuring parts of the stratosphere and above. And so you're limited to that kind of chemistry. So I think that's a pretty major limitation that needs to be addressed for now. So I apply this to when we do this experiment of, okay, if we're just looking at the very, very top parts of Earth's stratosphere and a similar scale height for a Venus atmosphere, what do they look like? And the scary thing is that at that height, they actually look pretty similar once you get above the ozone. So.
To be an enthusiastic, I think you've already answered it, but on Earth, if you look at the altitudes you're talking about, can you see a diversity of complex molecules, or is it already so simple that you don't see much?
I would say it's simple enough that you're not directly detecting necessarily the products of complex chemistry at that point. This is where some theory has come into play about people imagining ecosystems that are prolific enough that they can influence the atmosphere up until those very high scale heights. But at the moment, I think that's pretty limited. That's, by the way, that I mentioned that's a limitation of the current methods, but I think with direct imaging, things like the Hubble World Observatory, where you're getting emission spectra rather than the transmission spectra, then we'll be able to do a lot better.
Hi, Steve. Great lecture, by the way. I was just wondering, and I'm sure you're going to be talking about this in the next lectures, but in your definition of habitability, how do you take into account which appears to be the fact that the conditions for appearance of life on Earth happened in a very short period of time where Earth was pretty uninhabitable. So how does this enter into your range?
Yeah, this is, as I mentioned, this is really about the sustainability of those conditions. So yeah, like you say, well, the conditions for Earth very, very early in Earth history were obviously profoundly different than they were now. But it's relying at least that we did have an inventory of surface liquid water in order to enable that. So it's really about having that as a starting point, and then sustaining it, which by the way it's very tempting for me to start talking about Venus at this point, but I'll hold off for 24 hours. But because that's one of the major issues there about whether you can sustain those conditions. One of the ways in which one of my colleagues put it for Earth, he said, Earth of 1 billion years ago was not an Earth-like planet. You hear this phrase, Earth-like planet. And certainly if any of you were in a spacecraft orbiting our planet 2 billion years ago, you wouldn't even recognize it. You'd go, oh, I wonder what planet that is. You wouldn't recognize your own planet. So, it's interesting.
Okay, another question?
So if any students do have questions, when I speak, I will not entertain questions from the old people, including myself. So, no, I'm including all of the lecturers. So no students yet? Okay, so then I'll ask my questions. And the tip, there's a beautiful stained glass window that shows Urania right here. I think Marcelo knows where it is, in the old observatory. So you should take a picture of that for the Uranus mission. But my question is, so are there any gaps still that are real, given the known biases? When you showed your distribution of planetary sizes and orbital periods, there, I could draw a line, or I could see some gaps in some, or at least based on the periods. Is that real? Is that, and probably some masses too. So it's not a continuous distribumassive right?
That's a good question. This is kind of a poor diagram to show this. There is a better one that shows the mass as a function of orbital period, which shows distinct groups. There are gaps which are real because close-in planets are easier to discover than planets that are further out. And that means that any gaps that we start to see for planets which are relatively close to their stars, say in orbital periods that are less than 100 days, so anything, say, within this region, any gaps we start to see there are real, because if they were there, we would have seen them. And some of the gaps that we see, for example, you can kind of see a gap between this population of planets, and although it kind of scatters out, when you look at a mass period diagram, that becomes far more obvious. And it looks like there are cases where essentially planets are having their atmospheres stripped. And so either they become stripped cores, or they're able to maintain their atmospheres further out. So there definitely are gaps that we are seeing. There's a well-known gap, which is sometimes called the Fulton gap, after one of the main people who discovered it, P.J. Fulton. But it's a gap in the radius distribution that we now observe.
Thank you.
Another question? The last one?
Hello, thanks for your presentation. I'd like to know if you think habitability is a yes or no question, or there's more to it. I think you heard about the debate about whether habitability is a binary problem or no. Like, if we can say that a planet is habitable, like, or is there like a transition between that? Like, it's a scale problem, or it's a yes or no? Like, you can say that, okay, it is habitable, or like there's more to it. I don't know if I made myself understood, because ecologists tend to look like a lot of factors to make a planet habitable, and astrophysicists say that it is or it's not. So I don't know if you heard about this debate and what's your opinion on it.
Yeah, I think it's complicated. I think both viewpoints are correct from different perspectives. This goes back to what I said earlier about ecologists and astronomers come from different viewpoints, because the viewpoint of the astronomer on whatever definition we come up with, I need to be able to detect this from 100 parsecs away. That can impose a stringence on it, which doesn't allow for all of the ecological components. The ecological viewpoint can be sufficiently complicated that it ceases to have or has very little applicability from a remote sensing point of view. And so that's it. From listening to the various folks talk about this over many years, that's been my observation. But in terms of whether it's binary or not, I think that there are processes, and I'll talk about this tomorrow, actually, in the context of Venus. There are planetary processes that, if you have them or don't have them, can cause the planet to wildly swing one way or the other. And that is a possibility for the Venus and Earth dichotomy, insofar as I can use the word dichotomy when you only have 2 planets in your sample. Right? But they're very different from each other. And so I'll talk a bit about that tomorrow. But it's possible that there are various, certainly in the axis of time, when you look at a planet, you could see a planet transition. And that's something which has definitely been true of Earth. Earth has gone through many different transitions. We always argue about whether we would recognize Earth as a habitable planet at different stages of its history, but also true of Venus. But that's talking about how it's evolving through time. Whether you can look at a planet and say, well, based on my calculations, this planet is 73.5% habitable. Then I start to go, like when it comes down to metrics and things like that, I think because you're trying to compact too much information into one number, it just doesn't work. There's just too many factors at play to be able to say things like that. Does that answer your question?
Yes, thank you.
No,
My question was kind of similar because when we look at the TRAPPIST-1 system, most planets are in resonance or tidally locked. And I was thinking maybe we talk about habitability as a fully thing of the Earth, but it's infected with life everywhere. So my question was kind of similar to hers. Is there any possibility of like a tidally locked planet with just a ring of life on it or stuff like that? But it's kind of complicated, I believe, right?
It is very complicated, and there's been a few papers that have been written about this kind of Terminator habitability kind of scenarios that you're talking about. But there's a lot of possibilities. It's difficult to maintain these ring habitability situations because then you have a thermal movement of the energy budget of the planet and trying to take that into account. But it's interesting to think about the possibilities.
Okay, thank you. Just for curiosity, are you planning to talk a little bit more about ocean worlds in the next lectures or not?
Yes, I will be talking a little bit more about that.
Okay, so I'll keep my question for the next lecture. Okay, thank you. So let's thank again Stephen for the great lecture.